In this video, we're going to talk about antiderivatives. So, I want you to think about an antiderivative as really a puzzle. We're starting with the derivative, and we're asking, if we have a derivative, maybe it's 2x, what was the original function that we started with? How do we get back to that? What did we take the derivative of to get that 2x? So I want to think about a couple of different scenarios here. So what if we were to think about the function x squared over 2 plus 7? If we were to take the derivative of this, I'll call this f of x. The derivative of this would be 2x. Well, what if we had a different function, I'll call it g of x, that was x squared over 2 minus pi. If we take the derivative of that, that's 2x also. So you can see that it doesn't really matter what that constant is on the end, because that constant, when we take the derivative of it, is always going to be 0. So right now we have two different functions that give us the same derivative as 2x. Well, what if we go very generic and we look at x squared over 2 minus some constant c, and we take the derivative of that? The derivative is still going to be 2x. So when we integrate, and that's what it's called when we find the antiderivative, we're going to see some different notation here. So first off, I want to talk about this sign. That sign means we are finding the antiderivative. That's called an integral sign. The function that we're finding the antiderivative of is called the integrand. The dx tells us what we're integrating with respect to. And once we integrate this, typically we see the integral of f of x dx. And they call it capital F of x. That's what they use for the antiderivative. There's always going to be this constant of integration on the end. And that's because anytime you take the derivative of a constant, it's going to be 0. And we don't know what that constant is. That's called the constant of integration. But if we have enough information about that parent function, then we could figure out what that c value is going to be. And we'll talk about that a little bit later in the video. So let's talk about some basic rules for integration. First one is going to be our power rule. If we integrate x to the n dx, all we do is add 1 to the exponent and divide by the new exponent. Now this works as long as n is not equal to a negative 1, because that is a separate rule that gives us the ln function. So for example, let's say we want to integrate x squared. We're going to add 1 to the exponent and divide by the new exponent. And then we're going to have plus c on the end. Now with all of these, you can double check your answer by taking the derivative of what you just found, and it should be whatever this function is that you're integrating. So if we wanted to check that, we could take the derivative of x cubed over 3 plus c, and we're going to have 3 over 3x squared. The derivative of a constant is 0. And that's the same thing as x squared, which is what we started with. Our second rule is the e to the x rule. If we want to integrate e to the x, it's just going to be e to the x. The third one is the ln rule. If we integrate 1 over x dx, we're going to get the ln of the absolute value of x plus c. The reason the absolute value is important is because it affects the domain. Remember, when we take the ln of some function, whatever is in here has to be greater than 0. So we're fixing this domain and adjusting it so that it works for the problem. And then we have two other rules. One that says we could pull the constant out to the front, and then one that says that we can integrate each piece separately for adding or subtracting. So I just want to practice a couple of these. So what if we have the integral of 2x dx and we want to integrate? That fourth rule says that we could pull the 2 out to the front. And that's the same as integrating x dx. To integrate x, we're going to add 1 to the exponent and divide by the new exponent. And that's going to give us x squared plus c. Let's do another one. Suppose we want to integrate 3x to the fourth minus e to the x. Rule 5 says we could rewrite this as 3x to the fourth dx minus the integral of e to the x dx. So there's an understood parentheses here. And we could think about that as pulling the 3 out of the first one. So to integrate x to the fourth, we add 1 to the exponent, divide by the new exponent. And then when we integrate e to the x, it's just e to the x plus c. We always have that plus c on the end. Now you may be wondering, why didn't I add a plus c here and here? And let me show you why. We could say this is the same thing as 3x to the fifth over 5 plus some constant. And then when we integrate this, we would have e to the x plus some constant. And if I take a constant plus a constant, I still get a constant value. We don't know what that is. We're just going to call it generic c. So you'll get to the same place either way. You really only need one constant represented in there. Alright, so let's just work through a few problems. We want to integrate 2 dx. So we could think about this as 2x to the 0. This is going to be our power rule. We're going to add 1 to the exponent and divide by the new exponent. So we're going to have 2x plus c. If you want to check your answer, you can always check your answer by taking the derivative of what you just found. The derivative of 2x is 2, the derivative of c is 0, and that is the same thing that we started out with integrating. B is asking us to integrate 16 e to the t dt. Notice they've got a dt here that tells us that we're going to have t's in our answer. So I'm going to pull the 16 out. When I integrate e to the t, I get e to the t plus a constant. Looking at c, we have 3x to the fourth dx. We could pull that 3 out and think about just integrating x to the fourth. We're going to add 1 to the exponent, divide by the new exponent, and then plus c. So there's our final answer. D, we want to integrate 2x to the fifth minus 3x squared plus 1 dx. We could think about integrating each piece. You could think about pulling those constants out. So we're going to add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. And this is understood to be an x to the 0, so we're going to add 1 to the exponent, divide by the new exponent. Then you want to clean up. So this is really x to the 6 over 3. Once I reduce, minus x cubed plus x plus c. Final answer. And then let's look at that last one. We are integrating 5 over x minus 4e to the x dx. So we can think about integrating each piece. We could think about pulling that 5 out. And the 4 out of the second one. So that gives us 5 ln of the absolute value of x minus 4e to the x plus c. So there's our final answer for that. So let's make it just a little bit more interesting. Sometimes we need to use algebra to help us rewrite the problem before we can apply those rules. So let's start with A. We want to integrate 2x to the 2/3 minus 3 over x to the 4th. And we could rewrite that as 3x to the negative 4 and then use that power rule. So we're going to think about integrating each one separately. I do want you to notice that every time I rewrite that, each integral has a dx there. That's important to let the reader know that you're integrating with respect to x. Once you start getting into higher level math, you can integrate with respect to multiple variables. We're going to do single variables in this course. So I'm going to add 1 to the exponent. 2/3 plus 1 is 5/3. And I'm going to divide by 5/3. I'm going to add 1 to the exponent here. If I add 1, I get a negative 3. Divide by negative 3 plus c. Now we need to simplify this. Dividing by 5/3 is the same as multiplying by the reciprocal. It's your keep change flip rule. Negative 3 divided by negative 3 is a positive 1. So we're going to have 6 over 5 x to the 5/3 plus x to the negative 3 plus c. So in B, we are integrating 4 times the 5th root of w cubed dw. We can rewrite that 5th root as w to the 3/5. So we're going to add 1 to the exponent, which will give us an 8/5, and then we're going to divide by our exponent. Now we need to simplify this, so we're going to rewrite this as 5/8. The 4 and the 8 reduce, so we're going to have 5/2 w to the 8/5 plus c. In C, they're asking us to integrate x to the 4th minus 8x cubed over x squared. So to integrate this, we're going to have to rewrite this. We could think about this as x to the 4th over x squared minus 8x cubed over x squared. And then we can reduce that. So we're splitting that numerator. Okay. There is no quotient rule in integration, and there's no product rule. So that's important to remember. So something like this is going to require a rewrite in some way. So we've rewritten this, and now we've got it to where we can integrate it. So integrating x squared gives us x cubed over 3. Integrating x gives us x squared over 2. We can rewrite this as x cubed over 3 minus 4x squared plus c. And there's our final answer. And then let's do one more. Let's do e. E is asking us to integrate x squared minus 2 times x plus 3. There's no product rule, so we are going to have to distribute here. So we're going to have x cubed plus 3x squared minus 2x minus 6. And then we are going to integrate each piece. So we're going to have x to the 4th over 4 plus 3x cubed over 3 minus 2x squared over 2 minus 6x plus c. Simplify. And there is our final answer.